Okay, section 9.3, counting elements of disjoint sets. So we have three things to talk about in this section. And number one is the difference rule. And the addition rule. Don't know why I capitalized that one. Number two is we're going to talk about complement events. So if an event takes place, its complement, what that is, and how we work with that probabilistically. And number three is the inclusion and exclusion rules, or it's really one rule. / exclusion rule. So let's talk about what it means for two sets to be disjoint or disjointed. So two sets, A and B, are disjoint if disjoint doesn't have an E. So in math we say disjoint. You can say the two sets are disjointed or disjoint. So it doesn't really matter which word you use, which is why I started to write disjointed. But the property is the same. This means that A intersect B is the empty set. They have no overlaps whatsoever. And just a little reminder, absolute value of A, this is the number of elements in A. You can also see this as N of A. I think our book uses the N of A notation, number of elements of A, because absolute value is technically cardinality, but I'm going to use it interchangeably as with cardinality and size, just to keep things simple. So the reason we need disjoint is for our addition rule, sometimes called the subtraction rule or difference rule. So the addition rule says if A is non-infinite, so it's a finite set, and A equals A1 union A2 union ... union AK. So you can create a finite union of smaller sets that construct your largest set A. And all sets A sub I are mutually disjoint. So remember, this means that AI intersect AJ is empty. This would be for all I not equal to J. So that's what mutually disjoint is. So any pair of sets, any pair of these A sub i's that we could pick have nothing in common. Then the size of A is the size of A1 plus the size of A2 plus ... the size of AK, because there's no overlap. So to get all the elements, all the number of elements in A, we have to add up the number of elements in each of the smaller sets that construct A. So we can look at a little example to help us make sense of this a little bit more. And we'll stick with passwords for this section since that we started in the last couple. So let's think about how many passwords of length 3, 4, and 5 are there. So we're going to allow capitals, lowercases, numbers, and the following symbols: plus, minus, equals, underscore, less than, greater than, forward slash, backslash, question mark, exclamation mark, at symbol, number sign, percent, caret, ampersand, the star, left parenthesis, right parenthesis, left bracket, right bracket, left curly brace, right curly brace, vertical bar, semicolon, colon, quotation mark, apostrophe, comma, and period. So these are just all of the symbols that you can get from your keyboard. We're going to allow capitals and lowercases, all the numbers 1 to 9, or 1 to 9 including 0 at the end, so 0 to 9, and then all of these symbols. And we want to know specifically how many passwords can we make. Now, this is the only restriction. So you can repeat, you can do all that stuff, so we don't have to do any combination stuff. So the first thing you want to do is count up how many symbols we have. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29 symbols. If I counted those right? Now I'm not sure. Yep, 29. So we have 29 special characters. I'm going to switch colors here. We have 10 numbers, 0 to 9. And there are 26 letters. But we're going to times this by 2 because we can have lowercases and capitals. So that gives us a total of, what, 28, 30, 40, 57, 67 characters. Oh, wait, no, times 2. So 52, 10, and 29. So 91 total symbols. Now, if we want the length 3 passwords, we have 91. Since we can repeat whenever we want, this is cubed. Length 4 would be 91 to the 4th, and length 5 would be 91 to the 5th. And so we would just calculate that out and add that up, which comes out to be 6309649,983. So 6,309,649,983 combinations of passwords that we could construct with those alone. But if you think about as just your passwords that you make for any account that you're thinking about, we don't get all of those characters. A lot of times they don't let us use the curly braces and the brackets and the vertical bar and the backslash and the forward slash and the period. We're limited. And if you think about what you're limited to, a lot of times it's the special characters that are above the numbers. Now, that's not always hard and fast true because underscores are very common to be used, and so is the period. But it's never that many for 3, 4, and 5. And so this is just a way to think about the addition rule, though, because nothing overlaps between 3, 4, and 5. So we can just add them straight up. Now, the difference rule puts a caveat on our addition rule. I think I said the difference rule and the addition rule were the same earlier. Disregard that. That's crazy talk. So if the size of A is finite, so less than infinity, and B is a subset of A, then the size of A minus B equals the size of A minus the size of B, which is a fairly straightforward because remember A minus B is the set of things in A that are not in B. So just a little reminder here, A minus B is the set of X in A such that X is not in B. Just a little review there. So it makes sense that the size should be everything in A minus the number, or the number of things in A minus the number of things in B, because we want to take out all of those things from the subset. So let's take a look at another example similar to what we just did, but we'll make it a little bit simpler. So how many pins and we're going to allow for alphanumeric pins. Have repeated symbols. We're going to assume no capitals are allowed. So that means we only have access to the digits 0 to 9 and the lowercase letters. And then what is the probability that a randomly selected pin has repeated symbols? And we're going to use 4 digits in our pins, because that's kind of the standard. So we need to know 2 things. We need to know how many total pins there are, which we calculated in a previous section, and we need to know how many total pins there are that are unique. In other words, they don't have any repeated digits. So if we have a 4-digit code, we have 36 to the 4th total pins, allowing for repetition. And then we have 36 times 35 times 34 times 33. We're calling them unique for shorthand pins. So these are things that don't have any repeats, right? Once we pick our first digit, the next one excludes that from the choices, the next one excludes both of those, and the last one excludes the first 3. So we did this in the previous section. 36 to the 4th is 1,679,616. So this is the size of A. And 36 times 35 times 34 times 33 is 1,413,720. And this is the size of our B, so to speak. And so A minus B is 265,896. These are repeated. So if we want to know what the probability is that we pick one that has a repeated out of just selecting a random one, well, that's A minus B over our total A, or 265,896 out of the 1,679,616 that there are, or approximately 0.158, or a 15.8% chance. So there are very, very few with repeated symbols comparatively to the non-repeated symbols. And so you can think about this as when you're making a pin, if you use a pin that has a repeated digit or a repeated alphanumeric digit, there's a lot more chance that it can be guessed because there's a lot less of those in comparison to the total pins. So you want to always be choosing your passwords when you can to have all unique digits. It makes it harder to guess because there's just too many of them. So this kind of leads into our next topic, which is complements of an event. So we're going to be talking about the probability of an event complement. So if the set S is finite and S is a sample space, and A is an event in S, then the probability that A complement occurs is 1 minus the probability that A occurs. Now if we remember what A complement is, remember A complement is the set of things in our big set S such that S is not in A. And so by definition, A complement and A have to be mutually disjoint. And so it makes sense that the probability, if the probability of something happening is 100% or 1, you take a sample space, you run an experiment, something's going to happen. Well, the probability that nothing in A happens has to be exactly opposite the probability that something in A happened. So 1 minus that percentage. Now, a question that comes up when we're talking about complements like this often is, how do we find the number of elements of non-disjointed sets? All right, so the last couple things have all been about disjoint sets. They're easy to do because they're distinct. Nothing overlaps. Well, we have what's called the inclusion and exclusion rule to handle when sets do overlap. So this is the inclusion / exclusion rule. And it's fairly intuitive. So if A, B, and C are finite sets, then the number of elements in A union B is equal to the elements in A, the number of elements in A, plus the number of elements in B, minus the number of elements in both. And I say this is intuitive because if you think about A union B, if we just add up the stuff in each, everything that's in A and B that's in their intersection gets counted twice. So if X is in A and X is in B, it's going to get counted twice. Now we don't want to subtract both of those away from our count because we do need to count that element. But we know that the union doesn't list repeated elements, it just lists the elements that we see. So we subtract one copy, and if we just subtract the number of things in the intersection, that will subtract exactly one of those counted elements. And we can extend this to larger sets, or larger unions. So the size or the elements of A union B union C is equal to the number of elements in A plus the number of elements in B plus the number of elements in C, whoops, not parentheses, and then minus the things that are in A intersect B minus the things that are in A intersect C. I did it again. And minus the things that are in B intersect C. Now, something bad happens here. if there's an element that's in all three, so if x is in A, x is in B, and x is in C, it's getting counted here 3 times, but that element, which is in all three, gets counted here once, here twice, here a third time. Because x, if it's in all three sets, it's in the intersection between A and B, so one copy gets taken away. It's in the intersection of A and C, a second copy gets taken away. And it's in the intersection of B and C, so a third copy gets taken away. So now we're not counting that element at all. So to handle that, we add back in the number of things A intersect B intersect C. They're in all three. Now we don't have to do that here because there's no extra set to get counted again when we only have 2 sets. When you have 3 or more, you have to do this. And you can extend this to 4 sets, 5 sets, 6 sets. Every single time you add more intersections that you have to subtract and more intersections that you have to add back up. So let's take a look at a couple examples that make use of this, and that will finish out this section here. So let's look at how many integers is an E from 1 to 1,000 are multiples of 3 or 5. And then, how many integers? My goodness, I'm forgetting how to spell integers. How many integers are multiples of neither 3 nor 5? So we're going to construct a couple sets to take care of this. The first, since this is a disjunction, we're going to be looking at 2 sets. The first being the integers n, such that 1, n is between 1 and 1,000 inclusively, and 3 divides n. Then we also need to look at the set of integers n such that 1 is less than or equal to n is less than or equal to 1,000, again, in the right range, and 5 divides n. And so what we need to do is figure out how many of these exist. Now what we don't want to do is double count. So for instance, 15. 15 is a multiple of 3 or 5. It's a multiple of both. But we don't want to count that twice because there's only one number 15. So we need a third set, which is the intersection. We need to know how many are in both. So work with me, paper. So A intersect B is the set of integers n such that 1 is less than or equal to n is less than or equal to 1,000. And 3 divides n, and 5 divides n. So we can look at what happens to our set A. So if n is in A, that means that 3 divides n, so we can say 3a equals n for A in Z. And so A or n equals 3 all the way up to 999. So n isn't strictly equal to 3, but it could be any of those things. And just like we did in the previous section, this is 3 times 1 up to 3 times 333. So we did this when we looked at multiples of, I believe it was 5, from 1 to 1,000. So that means we want the size of integers, or the number of integers, from 1 up to 333. And we know that this is a total of 333, because we do 333 minus 1 plus 1 for a nice total of 333. And this will be the size of A. And so similarly, for the size of B, we look at n can equal starting at 5, which is times 1, all the way up to n can equal 1,000, which is 5 times 200. And so the size of B is the number of integers from 1 to 200, so 200 minus 1 plus 1, or just 200. And the size of A intersect B, well, we start with the first possible choice. So the first possible choice in A intersect B, I already said it, is 15. So it can be 15 times 1. And since this is the smallest number that is divisible by both 3 and 5, every other multiple of 3 and 5 together will be a multiple of 15. So you go to your highest multiple of 15, which turns out to be 990, which is 15 times 60. And so we have, or 50 times 66, not 60. And so we have our size of A intersect B is 66 minus 1 plus 1, or just 66. So now we have everything that we need. So the size of A union B, which is the number of multiples of 3 or 5. This is the number of multiples of 3 plus the number of multiples of 5 minus the number of times that they overlap. 333 plus 200 minus 66 equals 467 integers. And then the second part of this question was how many integers are neither multiples of 3 or 5, which means that they are not in either of these two sets, A or B. Well, if there's 467 integers that are one or the other, or both, that means that there are 1,000 minus 467, or 533 integers that are neither multiples of 3 nor 5. Because we know what our sample space is. It's 1,000. There's only 1,000 integers from 1 to 1,000. So our last example, again, we'll be just exploring this, counting up things, whether they're disjoint or not. So let's say that we have a class of 50 discrete students. And these students fill out a survey about their math history. So we have 30 that took pre-calc. We have 18 that took Calc 1. We have 26 that took Java. And we have 9 that took Pre-Calc and Calc 1. We have 16 that took Java and Pre-Calc. We have 8 that took Calc 1 and Java. And we have 47 that took at least one of those classes. Forty-seven took at least one. So we want to answer a couple questions. Now, for people who are going, well, that doesn't make any sense. The prereq is Calc 2. Don't worry, this is just for fun. And if it makes you feel better, pretend that some of these students took Calc 2 in high school, maybe AP Calculus or IB Calculus. So we want to know how many students didn't take any of the 3 classes. We want to know how many students took all 3. We want to know how many took Calc 1 and Pre-Calc. And then finally, how many took Calc 1 only? So the first one's the easiest, part A is the easiest. So if we want to know how many students didn't take any of the 3, well, looking at our list of stuff, we know 47 of them took at least one. So 47 people either took Calc 1 or Pre-Calculus or Java. And so out of our total 50, we can subtract away those to get 3 that took none of them. So that's just using our complement rule. And then for B, C, and D, we're going to set up a little thing. So I'm going to say P is the pre-calc students, the students who took pre-calc. C is the calc students. J will be the Java students. So in part B, we want to know how many students took all 3. So we want to know what the size of P union C union J is. So this is intersect P. Oh, I said we wanted to know this. We don't want to know this, but we're going to use this for a reason. So the size of P union C union J is the size of P plus the size of C plus the size of J. And as we know, this is going to be minus then P intersect J minus the size of P intersect C minus the size of C intersect J, and then add back in P intersect C intersect J. So I said we wanted to know the union. We don't want to know the union. We want to know the intersection. Now the reason we use this is because we know what all of these three things are. So the students in P, C, and J make up the students that took at least one, and that's 47. So there's 47 students that show up in total here, because we know that this construction will eliminate the overlaps. There were 30 pre-calculus students, 16 calculus students, 18 calculus students, and then 26 pre-calculus students, or Java students. Right? Yeah, 26 Java students. And then the students that took pre-calculus and Java, there were 16, minus the students that took pre-calculus and calculus, there were 9, and then minus the students that took calculus and Java, there were 8. And then plus that P intersect C intersect J. So we can use this to solve for what we don't know. So adding these up, we have 47, this is 39, plus the number we care about, P intersect C intersect J. And so that means that P intersect J intersect C, don't know why I changed the order, same but different. This is going to be 8. We're missing 8 students. And so this is our final answer, is 8. So to solve part C now, we're actually going to construct a Venn diagram. I don't know how to count. 30 plus 18 plus 26, this should be 41, which would make this 6, right? I think I did 16 minus 16. Yeah, I did. Okay, so this should be 6. So in part C, we're going to be constructing a Venn diagram. Looking at pre-calculus to calculus to Java students. So we know in the middle, there's 6 that took all 3. Now we know that from the problem, the number of students that took pre-calculus and Java that fall into this intersection is 16 total. So if 6 of them are already counted, there's only 10 here. For Java and calculus, we know that there's 8 total from the problem. So 6 have already been counted, so that means there's 2 here. And then for calculus and pre-calculus, there are 9 total. And so since 6 have already been counted, 3 have to go here. And then we just look at what's left. So we have 19 students counted in the pre-calculus category. We know that there's 30 total, so there's 11 left. In the calculus category, we know that there are, we have 11 counted, and there's 18 total. So we know that we need a 7 here. And then down in the Java students, there are 26 total. We have 18, which means we need an 8 here. So now we are looking at pre-calculus and calculus only. So P and C and not J. And I believe, yes, so this should have just been an only here. So make sure you add that back in. So P and C and not J. So those are the students that are in P and C but not in the Java category, so that leaves the 3 that are here. And then for D, this is P and not C and not J. So these are calculus only students, or I'm sorry, pre-calculus only students. What am I saying? I'm losing my mind. Calc 1 only, right? Calc 1 only. My goodness. So this is not P and C and not J. So these are the calculus students only, so there are only 7 of them there. So when you're working these problems, you want to start by finding the intersection, because you can build out and figure out what all the overlaps are if you know the intersection and then you know all the individual numbers. But that is going to be the end of 9.3 for us.